Hello Physical Science, this is Mr. B, and we are picking up today with section 3 of chapter 12, and now we're going to look at Newton's third law of motion, and associated with Newton's third law of motion is something called momentum. So we've talked about the first and second laws, so this section, section 3, is going to be split up into two parts, and it's going to hit on Newton's third and final law that we're going to discuss for now pertaining to motion. So to start this chapter, to kind of introduce it, or this section, I'm sorry, with our real life example, it has to do with bumper car, so something we can hopefully all relate to. It says when this bumper car collides with another car, two forces are exerted. Each car in the collision exerts a force on the other. So that's I think we've all probably lived that in our life. Hopefully at some point in time, even if you're the one with a lot of speed, you still feel a force exerted from maybe the stationary car that doesn't see you coming. So bumper cars, when you collide, each one exerts a force on the other, and that's going to be directly related to Newton's third law of motion, because according to Newton's third law, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. So when two things collide, they exert equal and opposite forces on one another. So if bumper car A hits bumper car B, bumper car A exerts a force on bumper car B, and vice versa, bumper car B is going to exert a force on bumper car A. So again, when two things hit, they equal and opposite forces on one another. And this is kind of known as an action and reaction force. So the force your bumper car exerts on the other car is the action force. So if you're the bumper car that has a bunch of speed build up and you're closing in on a person stuck in the corner that doesn't know what they're doing, when you strike them, you are the action force, and then the force that the car exerts back on you is the reaction force. And these two forces are equal in size and opposite in direction, which kind of makes sense. Sorry, got to close this out really quickly. Okay, so those two forces, they don't necessarily balance each other out. That's not what's going to happen here. We're going to explain why, but they are equal in size and opposite in direction. So we're going to do a couple other examples of action and reaction forces. So one simple example is, suppose you just press your hand against a wall. Your hand exerts an action force on the wall, so you're pushing against the wall, and then the wall is exerting an equal and opposite reaction force against your hand. So it's not like you're just going to push straight through the wall or anything like that. The wall has something to say about it, and it exerts a force back against your hand. And another example is a swimmer. So a swimmer pushing against the water is an action force, and the reaction force acting on the swimmer causes motion through the water. So the water exerts the force back onto the swimmer. So again, the action-reaction forces propel the swimmer through the water. The swimmer will push against the water, and the water pushes back against the swimmer. So that's an action-reaction force. So something happens, again, you kick your feet and you move your legs through the water. That's the action force. You are acting against the water, and then therefore the water is acting back against you. Now, one thing that I was kind of confused about with Newton's third law is when you go back to here and it says that the two forces are equal in size and opposite in direction. So that would almost, to me, sound like, oh hey, these forces are going to cancel out and nothing's going to happen. But that's not what Newton's law is saying. That's or Newton's third law. It's not what it's saying. The forces don't cancel out because the action and reaction forces do not act on the same object. So what this means is, so again, this was when I was kind of reading through this, I kind of got a little bit confused, but it makes sense. So it says, for the swimmer, why do the action and reaction forces not cancel each other out and produce a net force of 0? And that's because the action and reaction forces do not act on the same object. So when we go back to the swimmer, the action force is acting on the water. So if you're the swimmer, you're pushing against the water. And so then the reaction force is pushing against you. So the two forces aren't acting on the same object. It's not like the action and reaction force are both acting on the water. One's acting on the water, one is acting on you, the swimmer, and that's why they don't cancel out and equal 0. So don't get confused and think that Newton's third law means that no force is ever going to be produced, because everything just cancels out. The forces are acting on different objects, so therefore it's not going to cancel out. And again, We'll talk about that more in class, but don't be confused. Newton's third law doesn't say that everything's going to be canceled out. And one big word that's also associated with Newton's law is something called momentum. And a momentum is the product of an object's mass and its velocity. So when you multiply mass and velocity together, you're going to get momentum. An object that has a large momentum, an object will have a large momentum if the product of its mass and velocity is large, which is just kind of common sense right there. So make sure you write down what this definition of momentum is right here. And just kind of some common sense things. I think hopefully we've probably heard the word momentum before. An object with a large momentum is harder to stop than an object with a small momentum, and the momentum for any object at rest is 0. So if you have a boulder and you start at the top of a 200-foot hill and you roll it down, by the time it gets to the bottom of that hill it's going to be pretty hard to stop. Whereas if you just started 20 feet up the hill, it's going to be a lot easier to stop because it's not going to have as much of a velocity by the time it gets to you, so its momentum is not going to be at large. But if it's just sitting there, not moving, its momentum is 0. And just some calculations that we can make for momentum, which we will do in class one day. I'm not exactly sure when, but mass is measured in kilograms, velocity is measured in meters per second, so momentum is measured in kilograms per meters per second. And we'll do some examples in class to show how we get to this label right here. And then this is our actual mathematical formula, which we kind of already said in words a second ago, that momentum equals mass times velocity. And so we'll just give a quick example of momentum. Again, hopefully we might even know the answer off the top of our head before we even go through the calculations. We're going to go through a sample momentum problem. Which has more momentum, a 0.046 kilogram golf ball with a speed of 60 meters per second, or a 7 kilogram bowling ball with a speed of 6 meters per second? So we notice the golf ball has a much higher velocity, but the bowling ball has a much greater mass. So we're just going to work it out. The momentum of the golf ball, you just take 0.046 times 60 meters per second, and you get 2.8 kilograms meters per second. So that's 1, and then we go, hopefully we can see now what 6 times 7 is going to give us. 6 times 7 is going to be 42, and obviously the bowling ball has a much greater momentum than the golf ball. And I would probably write that down. I'll probably ask you on your quiz what had the greater momentum in the sample problem, and you need to know that the bowling ball had the greater momentum in the sample problem. So that is it for the first part. Again, we're just introducing action and reaction forces and how we actually calculate momentum, and we'll finish off with more about momentum in tomorrow's video. So let me know if you have any questions.